Okay, so I'm looking at page 8 in the guidebook, and as page 8 says, you have to determine which substance is more polar. So we have degrees of polarity, and we can figure out what those degrees are. So the first one you have here is carbon disulfide. So first step is to draw them. We know this is nonpolar. And then I have sulfur difluoride. So sulfur difluoride looks like this. It's still linear. And if you can't remember how to draw them, you can look back at the video that I did for homework. I believe that was on covalent page 2. Yeah, the one in that chart. And your rules are on page 2 as well. So in this case, the one that's going to be more polar, odds are it's going to be the one with the fluorine in it, right? Because that's the most electronegative element. I can look at, they're both linear, so that doesn't help me. I can look at my electronegativities though. Carbon is 2.6, sulfur is 2.6, and obviously there's a bigger difference here, where this is 4. So this is going to be a much more polar substance because of that electronegativity difference. It's probably not going to be exactly linear. It probably will be slightly bent, maybe in one direction or the other. Number 2 is nitrogen trichloride versus oxygen dichloride. So oxygen dichloride is going to have a similar setup as sulfur difluoride. And this one is symmetrical, as is this one. The one above it is also symmetrical. But yet we decided this one was more polar than that one based on its electronegativity differences. This is symmetrical as well, whereas this one is a little bit asymmetrical. I've got more electrons along the bottom than I do on the top. So this is going to be the one that is going to be more polar. Number 3, boron trihydride. This is a flat molecule, so it's like a triangle. And boron is a little different. You don't actually have to worry about knowing this, but I'll just show you. Boron actually prefers, is an exception to the 8 rule. It prefers to have just 6. So it'll set up like this, and it'll be flat and in a triangle, versus ammonia. So ammonia, we already know, is a very polar molecule. So picking between these two isn't so hard. This one will be more polar than the other. When I look at the next one, let me erase some of these. So chlorine diatomic, that's really not polar. Versus phosphorus trichloride. So here's my phosphorus. Phosphorus likes to bond like nitrogen does because they're in the same group. So it's going to have the 2 electrons up here. Hopefully you guys are seeing some patterns. So phosphorus and nitrogen like to make this trigonal pyramidal shape. This one's obviously more polar. Silicon dioxide. Now silicon dioxide, you could argue it being polar, or sorry, being ionic or being covalent. The Regents likes it to be covalent. I'm not sure why, because glass chemists like it to be not covalent, but ionic. So I guess it just depends on how you want to look at it. So this is silicon dioxide, just similar in shape as silicon, as carbon dioxide. They're in the same group. There is an electronegativity difference here, 1.6 versus 3.4. And then we're looking at carbon dioxide. So carbon, the electronegativity difference. So here's my 3.4, but I'm much closer, and this is 2.6. So this electronegativity difference leads me to think that this one is going to be more polar. Methane is just CH4. This one's pretty nonpolar, as you can see. No electrons, even distribution. And then if I throw in a couple of chlorines, and you could put the chlorines anywhere around the C. So if you wanted to put them kind of like this, or you could put them right next to each other. They actually do kind of rotate around a little bit in real life. And in this case, because these chlorines are present, this would be the one, if you had to pick between those two, that would be more polar. Not necessarily completely polar, but definitely more polar than the methane. We got two more. Silicon tetrabromide. Again, silicon's going to bond a lot like carbon because it's in the same group. That silicon I looks like a dot. So this is looking pretty nonpolar versus HCN. Now, how did I get this structure? Well, I've got one valence electron here, I have 4 here, and I have 5 here. That gives me 10 electrons. So if I start from scratch, and I just kind of carbon likes to be in the middle, I'm going to give my outside atoms the ones that they want, right? Hydrogen wants 2, carbon wants 8, and I've used up all of my electrons. So I can put my line here and here. But my carbon is very not happy because it only has 2 lines and it wants 2 more. So I'm going to move these electrons in and these electrons in so that I ultimately get this molecule. And obviously this one is going to be a heck of a lot polar due to its asymmetrical distribution of electrons. And then lastly, I've got nitrogen trifluoride. Versus phosphorus trifluoride. So it's going to look very similar to the other one. So at this point, shape's the same. The only thing that's different is a nitrogen versus a phosphorus. So let's look at those electronegativity differences. We know phosphorus is 4, or sorry, fluorine is 4, phosphorus is 2.2, nitrogen is 3. So the one that's going to be more polar than the other is this one right here because of that electronegativity difference. All right. That's it for page 8.